in the main menu. Today I have spoken with Professor Dieci, and we will continue in integrals to develop integrals and computations, so maybe some generalized integral with limits that we didn't had last time, and maybe if we have time we will perform some different simple differential equations. Okay, so let's begin with this kind of integral. Wait a second. I will share my Blackboard with you as usual. Okay, so let's do some evaluation. We begin with we can use some integral that we had last time, maybe. No, okay, no problem. Then we will perform this one. Okay, I found my pen. And so we begin with this kind of integral.
Sorry, can you record the lesson?
Oh, yes.
Thank you.
Of course. Okay. Okay, now it should be recording. Okay, recording. Okay, so now we will begin with some integrals where we have extremal points that are to evaluate, but with some limits. For instance, I think we had some similar integral, but without this kind of solution. So if you recognize something that we already did, let me know, because maybe I use different exercises for all my courses, and sometimes I have same kind of exercise. So this is an integral where we should compute a limit, because we cannot explain plus infinity as a number. So the meaning of this one is to choose a number b such that, first of all, we evaluate in for the value b some positive number, I would say, and then once we have computed the integral, we can compute the limit of the integral. So that is the meaning. So that means we can concentrate and take the limits after the computation. Okay, so which kind of integral is this? We've seen something similar, I think last time. It is useful for infinite series and fractional integrals, where we have algebraic polynomial over the fraction and under the fraction. We need to split this second order polynomial, and consequently the fraction will be a sum of two fractions. So first of all, we compute the roots of the polynomial, but I think it is very simple because this is special trinomial where you have the sum of two numbers that gives 4 and the product of the two numbers that gives 3, and these two numbers are 1 and 3. X plus 1 times x plus 3 is a factorization of this polynomial. If you don't find immediately a factorization, you can use the rule where you have the second order polynomial and solve the second order equation with the quadratic formula, where delta is b squared minus 4 times a times c. And if delta is greater or equal to 0, you can x1 and x2 are the two roots of the equation. You can split this product. You can split this polynomial in the product of these two parentheses. Of course, we didn't have, we had 1 as a factor in front of the first term of the polynomial, so that means it is 1 times these two parentheses. So then we have, instead of this fraction with the polynomial, we have a fraction with two factors, x plus 1 times x plus 3. What is our goal is to obtain a sum or a difference, something that we can evaluate, where one denominator is x plus 1 and the other is x plus 3. And what we have? Something that is unknown, let's say a and b. But as you know, the rules for in order to obtain again the sum of two fractional expression is to find the least common denominator, and once we have found this, we should obtain something that equals 4. But in order to do that, we should multiply the numerator a for the factor that is missing and the denominator x plus 1, and that we have by the least common denominator, and that is a times x plus 3. plus b times x plus 1. This is the result of the sum of these two fractions. We can rewrite everything as coefficient of the variable x, and something that is of degree 0, and then we have to compute by choosing everything that is on the right side equals to 4. That means this numerator 4 should be exactly this expression. Thanks to the fundamental theorem for polynomial, that means that everything that multiply 4, everything that multiplies x should be 0, because you can see this polynomial as something that has x to the power 0 times 4 plus x to the power 1 times coefficient 0 plus plus plus. You can see it as a polynomial where the only coefficient that remains is the coefficient of the 0 degree. And what we have on the right side, someone wrote something? No, okay, I hear some sound. Okay, that means that we have the 0 terms, so x to the 0 power, and that is what has all the terms that don't have x, 3a plus b. Okay, this is 1, of course. It is only a notation to understand the meaning. And everything that has coefficient 1, that is a plus b, and so on. This is everything that we have on the right side that should be equals to 0. I choose different colors. So this should be equals to 4, and this should be the coefficient of x to the power 1 of x. Okay. So this gives us a system in two variables. That means that 3a plus b should be 4, and a plus b should be 0. So from the second one, we can compute minus a equals minus b, or b equals minus a. It is the same, and we can substitute instead of b minus a on the first equation. And so we obtain 3a minus a is 2a. 2a equals 4. That is as a equals 4 divided by 2, because I can then divide by any side. So a is 2. b is minus a, so it is minus 2. We have found these two numerators that we can put instead of a and b inside the integral. I think this is clear because this is all computation. So next step is to write this integral as a sum of two integrals. That means that we have limit for b approaching to plus infinity of the integral from 0 to b of divided by x plus 1, and I can split the sum, as I said before. I can split the sum and compute the integrals of the sum as the sum of the integrals. This holds only for sums, not for product. Don't forget. So I will use the parentheses, so I don't need to rewrite the limits, and then we can write minus 2 divided by x plus 3 in the x. Okay, what are these two integrals? If I don't consider the numerator, but only 1 over x plus 1 in the first integral and 1 over x plus 3 in the second one, I can use the rule for the logarithm of x or logarithm of some expression, because as you remember, you can write 2 as you can factorize out 2, and you can write 1 over x plus 1, and this is exactly the logarithm of the absolute value of the denominator. Because if we differentiate this expression, the derivative is 1 over x plus 1 times the derivative of the argument. X plus 1 has a derivative only 1. So this is what we use in this integral. Okay. That means I can rewrite 2 times the natural logarithm of x plus 1 between 0 and b minus 2 multiplied by natural logarithm of x plus 3 computed by between 0 and b. Okay, this is the expression that we should compute. So, limit for b approaching to plus infinity. Now I can write this parenthesis because I don't know any computation. So we have a logarithm of b plus 1 minus a logarithm of 0 plus 1. And as you know, 0 plus 1 is 1, and logarithm of 1 is 0. So what remains is logarithm of b plus 1. Okay, then we have in the second one minus 2. We have this time logarithm of b plus 3 minus 2 times minus is plus 2. No, okay, I did write the parentheses, but I think it is better to write everything. So I will write minus 2, and then minus 2 times minus is plus 2. Logarithm of 0 plus 3. Of 0 plus 3 is 3, and the absolute value of 3 is 3. Okay. As you know, we should compute the limits. But if you If we take a look at these terms in the parentheses, we will notice that plus logarithm of plus infinity is going to plus infinity. Logarithm of plus infinity is going to plus infinity, but this is a minus 2 times something that is going to plus infinity, so we have a form that we cannot decide where it is going. But we can rewrite by taking out the factor 2. We can rewrite this difference, so it is 2 times logarithm of b plus 1 minus logarithm of b plus 3. That means I can use the rule of the logarithm and then substitute the absolute values that poles are absolute value minus 2 times logarithm of 3. Okay. Now, where is going this fraction? If you compute the limit of this function for b approaching to plus infinity, it is it is 1, because you can rewrite the exponent of the variable b is the same both under and over the fraction. You can rewrite if you want, if you use the usual rules, you can rewrite as 3 over b. That means every parenthesis is going to 1, and you can cancel the factor b, so this is 1. Okay, so this limit is 1. That means that this limit, it is for b approaching plus infinity, logarithm of 1, that is 0. So it is 2 times 0 minus 2 times logarithm of 3, because logarithm of 3 is a number that is independent from the computation of the limits, because there is no b inside the expression of this term. And if you want to write this factor in front of the logarithm as exponent, I'm sorry, it was a plus, okay, plus from this computation, you can write a logarithm of 3 squared, that is logarithm of 9. And this is the solution of this computation of this integral. So the limits comes only at the end, and normally it is very easy. So let's do some other computation. I had some integrals. For instance, some definite integrals, maybe with maybe we can use integration by part or substitution. And let's see, let's compute. Okay, so which kind of computation is allowed? As we know, to perform integration by part, we should find two functions that are multiplied, for which one of the two functions is easier to differentiate and the other is easier to be found as a primitive function to integrate, so to speak. We've seen last week, that we had integration by part for this product exponential function times a power of x. As we computed, it was an integral where we consider the function exponential easy to integrate, so easy to find a primitive, and the function x cube easy to differentiate. We did perform twice the computation, and we ended up with many integrals, but in the last integral there was only the exponential function, so it was easy to integrate. In this case, now, okay, in this case, it is the contrary, because as you know, logarithm of x or logarithm of something else is not easy to integrate because we don't know a primitive of the logarithm. We know that the primitive of a logarithm is it is possible to compute by performing integration by part. So in this case, the factor logarithm of 2x is the factor that it is easier to differentiate. Okay, so let me use the same letters that we did use last time. That means F and G. So this rule. Okay, so we use the same letters for the functions. Okay. So, what is F and what is G? And what is G prime? F is something that it should be easy to derive, to differentiate, and we choose as F logarithm of 2x. That means that we should compute F prime, and that will be 1 over the argument of the logarithm multiplied by the derivative of the argument. So this is 1 over x. And what we consider as G prime is x cubed. That means that we want to integrate x cubed, and this is x to the 4th power divided by 4. So now, with this computation in mind, we can apply the formula f times g. So logarithm of 2x times the function, and maybe I write on the left the function x to the 4th divided by 4, so there is no reason to confusion, and we should compute between 1/2 and e⁻, minus the integral between 1/2 and e⁻ of f prime, so 1 over x, multiplied by g, x to the 4th divided by 4. And as you can see, we have a power of x that we can simplify. So x to the 4th becomes x to the third, and this x is going away. So we have one exponent less. So let's write equals. We should compute already this primitive in e half minus the same function in 1/2. Okay, so it is x to the fourth. So it is e divided by 2 to the fourth divided by 4 times logarithm of e, because 2 times e half, it is e, minus 1/2. One half to the fourth divided by 4 multiplied by logarithm of 2x divided by 2, it is 1. Okay, this is the first computation. And then we can write this integral, it is x cubed divided by 4. And we can already write the primitive, it is x fourth divided by 4 times 1/4. And we should compute between 1/2 and 8/2. So let's go on with the computation. We have that the logarithm of 1 is 0. So this whole term is equal to 0. It remains e to the fourth divided to the fourth times 1/4, because divided by 4 times the reciprocal, and the logarithm of e is 1. So this is the first parenthesis. Minus 1/4, we can put 1/4 outside, and compute again e fourth divided by 4, 2/4, sorry. Okay. Divided by 4, this is times 1/4, minus everything computed when x is equal 1/2. So it is 1/2, because it is 1/2 to the fourth, divided by 4, this times 1/4. This multiplicative factor 1/4, I put it outside and in front of the parentheses, okay? So there is no changing in the evaluation of terms, only it was easier to compute. So what do we have? We have the very same expression there and there inside. So it is 1 times this expression minus 1/4 the same expression. It is 1 minus 1/4 times e to the fourth divided by 2 to the fourth times 1/4. Okay. And then you have the last term, there is no e, so it is minus 1/4 multiplied for minus by minus, so it's minus by times minus is plus, so it is 1/4 times 1 to the 4 times 1/4. But it is 4, it is the same as to write 2 to square. So what we have at the very end is 4 minus 1 is 3/4. So 4 is again 2 square, so 3 divided to square times e to the 4th divided 2. And if we rewrite everything as a power of 2, we will have it is the very same denominator, because it is 2 plus 4, it is 2, it's equal to the 2 square, so it is 4 plus 4, it is 2 to the 8, and this is the same, it is 3, 4, 8 plus 1 divided by, if there was a mistake, so we have 1 over 2 to the 8, 3 e to the 4th plus 1. I think this is as compact as possible as solution. You can compute to the 8th, it is so 2 to the 5th is 32, then we have 2 to the 6th is 64, 2 to the 7th is 128, and then we have 256. That should be 256. Okay, but it's not important, because what was important is the computation of the integral. Okay, let's do another one. I think it is everything is clear, because I don't see any messages in the chat, so I will go on and compute some other integrals, and then we can switch to some differential equations. So let's use some variable substitution. For instance, we can compute this one, okay, or this one. I can let you, you find on the book of the Sitzreiter all these kind of integrals. Many of them have some written solution in the student's book without all the steps, but it is not mandatory. Okay, so what do we have? In this case, we want to perform variable substitution, okay? Variable substitution. That means that we choose something that is difficult to compute, and we substitute with some other variable that it can represent our difficult expression. I would write the whole denominator as a variable t equals 9 plus square root of x. Pay attention to the extremal point, 0 and 25. 0, it isn't something that gives you a 0 on the denominator, because it is 9 plus the square root of x. So we don't need to put the limit on this side, okay? So then t minus 9 equals square root of x, and if we perform the square of the left hand side, we have the square of the right hand side, that is x. Why it is useful? Because if we differentiate the right hand side, we obtain 1 times dx, and if we differentiate the left hand side, we obtain 2 times t minus 9. raised to the power of 1 in dt. That means that we can substitute the x in this expression in a very easy way. Okay, so that means, I forgot that we have to change so the lower bound of integration, that is 0. When x equals 0, then t is equal, we can use this expression, 9 plus the square root of 0. When x is 25, then we have t equals 9 plus the square root of 25, that it is 5, so we have 14. So we are ready to integrate this one. We have the integral between 9 and 14 of 1 over t multiplied by the x, so that is 2 t minus 9 in dt. And yes, this is the derivative. This is the reason why I didn't vote the expansion of this quadratic formula, because it is a power 2 times 2 minus 1 is the exponent, then we have to multiply by the derivative of t, that is 1, so we have this integral. And we can split the integral, because we have 2t minus 2 times 9, and we can write every fraction with its denominator, and so we have minus 9 over t, 2 times 9 is 18 in dt. And we can evaluate immediately the two integrals, because we can simplify t over and under the fraction, and then we have 2 times something. 2 it is seen as a constant. That means that we have to integrate, and the function, the primitive of 1 is t. This is the first one. The second one is 18 divided by t, as 18 times 1 over t, and we have again the logarithm of t. So minus 18, the natural logarithm of the absolute value of t, computed between 9 and 14. Okay, so then we have 2 times 14 minus 9, because we can substitute the values directly instead of t, minus 18 times logarithm of 14 minus logarithm of 9. That means 14 minus 9 is 5, 2 times 5 is 10, 10 minus 18, and if you want to use the rule for the difference of two logarithms, we have to write as a quotient 14 over 9, so logarithm of 14, 9. So, and this is the solution of this computation of the integral. Not too difficult. Okay. Maybe we can perform last integral, maybe this one, or this is by part. You can use, you can compute every kind of integral, but the rules are always the same. So let's complete the S1. Okay. So in this case, we have, of course, to substitute the limits because it is plus infinity. So this integral will be the limit for b approaching to plus infinity of the integral between 1 and b of this quantity. Okay, so what we perform is to substitute again something that is difficult, some difficult expression with a switching variable, and we take t and we put square root of x equals t. In the previous case we had yes, we can switch and we can choose this variable t. So that means t square is equal x. That means 2t dt equals 1 in dx. And the extremal point of variables for x equals 1, we have t equals the square root of 1, so 1. And for x equals b, we have t as the square root of b. We can put a different name. Let's denominate, C is for the constant. Let's denominate d, because if we rewrite the limits, we can choose that even the square root of b is approaching to plus infinity when b is approaching to plus infinity. Okay, so we only put a different name of but the meaning is the same. Yes. Also, we have e to the minus t divided by t and multiplied by 2t in dt. And as you can see, we can simplify the factor t over and under the fraction, and we remain with this computation limit for the approach to plus infinity of 2 e to the minus t in dt between 1 and d. So this is, if you want to evaluate the integral, this is, its primitive is e to the minus t, but if we derive, we obtain a minus in front of e to the minus t, so it is 2 multiplied by minus e to the minus t, and that is has to be computed between 1 and b. So limit d approaching to plus infinity. So the first one is minus e to minus d minus then plus e to minus 1. Okay. So what is this limit? E to the minus 1 doesn't depend on our constant d. The constant is going to plus infinity. That means that everything is on the exponent minus infinity. And as you know, when e is approaching, when the argument of the exponential function is approaching to minus infinity, the exponential function is going to 0. So everything that remains is 2 times e to the minus 1, that is 2 divided by e. This is the final solution. Okay. Okay, I think we had an extensive amount of computation, and we can switch and try to compute some types of differential equation, some simple types of differential equation. First degree linear differential equation. Let's take some example, some simple example that you have maybe in your book. Something very simple. Okay, I think you've seen this. Oh, I've already chosen some example from the book, and maybe we can begin with let's begin with something easy. Because I don't think you did compute something with separable variable, but we can use this kind of equations. Okay, so let's begin with this one. This is right. Okay, so this is a very simple computation of an integral of a differential equation because we don't have the term b. As you've seen by the rules, you can always compute by integrating the terms of this type of equation, x x dot plus ax equals to b, and the solution is x equals to some constant c. If you don't have any boundary condition, that means if you don't have something where you can substitute a value, that means you cannot compute the constant c, and this is e to the minus at, because as you know x is a variable that is depending of t, and x dot means dx over dt, and this is the solution that you know that is easy to compute. I think you already seen in the lectures of Professor Dietri. So what do we have? We have a and x dot plus 3x equals 0. That is, we can put, instead of a and b, the values a equals 3 and b equals 0 in the solution. So it is c a to minus 3t plus 0, because b is 0, 0 divided by 3 remains 0. So, how this expression affect the solution of this differential equation? And the steady state is stable, because if you want to compute, c is some constant, of course. If you want to compute the limit where t is approaching to plus infinity, we have a that is negative. That means it is something that is going to 0. Okay. If we have had, for instance, this kind, x plus 3x equals, I think we have an exercise. Equals something, let's say 18. Okay, so we have a equals 3, b equals 18. So the solution is x equals c multiplied by e to the power minus 3c plus b divided by a. That is 18 divided by 3. That is 6. So it is c e to the minus 3t plus 6. The steady state is approaching to 6, because this limit at the first term is going to 0, for t approaching plus infinity is going to 6. Okay, d 5 x dot plus x equals 0. You can divide everything by 5, and you can rewrite x dot plus 1/5 x equals 0. And that means that you can write the solution as x equals c times e to t fifth, because a is 1/5, b is 0. This is not a solution that converges, because we have t fifth, but for t converging to plus infinity, approaching plus infinity, This tends to plus infinity if c is greater than 0, to minus infinity if c is smaller than 0. Okay. Okay, I think everything is very simple and clear. So let's perform some other computation. We can use, for instance, this. Maybe this. This is the kind of variable that hasn't constant coefficient, but on the other side we have a function of t. Okay, this is this kind of equation. That is this type, x dot plus ax equals to something that is not a constant and depends on t. Maybe you didn't. Okay, we will do this simple example, but maybe I will return to the previous one where there was x squared. Okay. So, what is the meaning of this expression and what is the solution? The solution is given by the computation where A is 1/2 and B of t is e to the power of t. B of t is called the forcing term. You have two ways to compute this kind of differential equation. You can apply directly the computation that is given as a rule, or you can evaluate the equation, the general solution of the equation that is homogeneous, so without this term that is associated. Okay, you can do this computation. Okay, that is simple to compute, and then you can add a function as a particular solution and substitute computing the derivative. But I think it is very simple to remember the formula for this computation, because this is obtained, so the second way I prefer is this type of solution, because it is very easy to remember, but I will explain the steps. If you multiply everything by e to at, then you will have that, of course, on the left hand side and on the right hand side. Then you will have this expression that corresponds to the derivative of the product x times e raised to the power of at. Okay, this is the derivative with respect to t. Okay, because you have the derivative of x with respect to t, this x dot, multiplied by the exponential function plus x as it is multiplied by the derivative of the exponential function where you have to derive a times t and you have a coefficient a in front of the rest of the derivative. Okay, that means that if we integrate both sides, so we compute the primitive at both sides. Of course, we have to add the constant c. So this one will be x multiplied by e to raise to a t. So that means x, because we have the constant, equals the integral of b plus c. Okay, and now you can multiply everything by the inverse, by the reciprocal function of this one. Okay, it is the same as divide by, so yeah, multiply by t and then divide by, on both sides, of course, EAT. So that means that x is equal 1 over e to at, it is e to the minus at, and multiplied by everything as it was before. Of course, you cannot put outside or inside. I didn't write it. T plus c multiplied by e to the minus 80, because we multiplied everything on the left hand side and on the right hand side. Okay, by taking into account that it is the kind of solution that we can use for this type of differential equation, we will solve following the rule. Okay, so the first method is to computing the general solution to the homogeneous equation. Okay, and this will be of the type of the exponential. And then taking particular solution with the general solution of the homogeneous function, homogeneous equation, and choose a new function that is written as an exponential function again, and putting equals to the forcing term b of t. But as I said before, it is easier to compute with the formula. So let's take x and write down the solution. What is a? A is 1/2. So we have a to the minus 1/2 multiplied by t, and then integral of b of t. This is this forcing term that we have above, multiplied by e raised to a times t, raised to 1/2 times t in dt, plus c times e to the minus 1/2 t. Okay, so let's divide everything. Okay. So this is the general solution on the right, and we will solve the differential equation on the left. So then x is equal e to the minus 1/2 t multiplied by the integral t plus 1/2 t, because it's the sum of the exponential. It is 1 plus 1/2, it is 3/2 t in dt plus the constant multiplied by e to the minus 1/2 t. The primitive function of e to the raised to 3/2 t, if we differentiate this function, it remains e to 3/2 t, but we have to multiply by the derivative of the argument, that is 3/2. Okay, so that means we are missing 3/2, and we can put 3/2 inside the integral multiplied by 2/3, or write directly, in this case, the primitive function of e to the 3/2 t multiplied by 2/3. That means divided by 3/2, okay? And plus c multiplied by e minus 1/2 t, okay? So what we have to do is rewrite the solution, because we have a multiplicative factor 2/3 that we can put in front of this product, and then we can summarize the two exponent, minus 1/2 t plus 3/2 t plus c e to minus 1/2 t. And as you can see, 3/2 minus 1/2, it is 1. So this is e to t. Let me cut out this derivative, that, and then I can cancel and rewrite so that I can use this room. So this I can put inside something that is transparent. Not there, but there. And then okay, and then go on by using writing down what I said before, 2/3 times e to the t plus c times e to minus 1/2 t. Okay, many times you have to compute a particular solution by substituting a value that x or the derivative of x is taking is given from the textbook, and then you have to substitute, and you have to compute by substituting variable t, and then computing what you have inside. So let's do this example that has a rule that you can directly apply, that it is given even in your book. It is this one. Okay, this one. This almost the same of f, and we could choose the 30 square, but maybe I can let you as an exercise the other expression of the differential equation, and you can try to solve them. Okay, this is a very typical type that is given to you as this solution, and you have x dot plus ax equals, this time b is a constant, it doesn't depend on t, but you have this x squared. Okay, you can apply the rule, and maybe you had an explanation during the lesson, but this is a kind of solution where x, sorry, okay, there we go, x is equal a divided by b minus some constant c e to the power of a times t. Okay, so you have c, or you have a, or you have some similar expression for this solution, because it is something that means only a constant. So let's compute the solution of this equation. We have that a is equal minus 3 and b is equal 12, so you can write directly the solution. F is minus 3 divided by 12 minus c e to minus 3. Okay. For t approaching to plus infinity, this term will be 0. So it doesn't depend on your constant, and this will be will remain. So this is approaching to 0. 12 minus 0 is 12, so it is minus 3 over 12, so minus 1, 1. Maybe you want to see another type of this one. Maybe we can compute. Oh, I think we had a lot. Something that is not so difficult. But I can give you a very okay, let's do this one, okay, because I think maybe this is something that you need to apply more than once. This is the same type of this one. I can put new word. Then we can apply once again the rule, and maybe I can show you how to solve some easy with separable variables. So, we use the rule that is x equals e to minus at, a is 3, multiplied by b of t, which is t squared, times e to plus 18, 3t. Plus c multiplied by e to minus 3t. Okay, what we have to do, so we can exercise, is to compute this integral. This integral is very similar to the type that we've seen at the very beginning of these slides, where there is a power of the variable and you have to perform integration by part. Okay, by part. So what is in this case easy to differentiate and easy to integrate? Let me use the same letters as before for the integrals. F times g prime. Okay. Okay. So we have f and g prime. So f prime will be 2t and g will be e to the 3t divided by 3. So this is equal f times g, so t squared times e to the 3t divided by 3 minus f prime times g, 2t times e to the 3t divided by 3 in this case. And then again we should perform integration by part. So that means that this remains the same. Of course, if you have to compute the integral with lower and upper bound of the integration, you have to compute in this term too. But you can take out 2/3 and rewrite this integral as t times e to 3t in dt. That means that you again consider f and g prime, so that f prime is equal 1 and g is equal e to the 3t divided by 3. Okay, so at the very end you will have t squared times e 3t divided by 3 minus 2/3 multiplied by f times g, that means e times e to the 3t, minus integral of f prime times g, integral of 1 times g is this integral that you can evaluate immediately, because it is 1/3 multiplied by e to the 3t divided by 3. So at the end you will have, so this is 3t divided by 9 in this case. So what do we have? We can take out e to the 3t and then write everything else inside the parentheses. T squared divided by 3 minus t, and we have 2/9. Let's write 2/9 in front of t. 2/9 times t. Minus times minus is plus. 2/3 times 1/9, it is 2/27. Okay, so this is your integral. That means that we can put the solution of the integral on the left hand side. Let's write so we can then we have x equals e to the minus 3t times e to 3t times everything is in the parentheses, t squared divided by 3 minus 2/9 t plus 2 divided by 27 plus c times e to the minus 3t. Minus 3t plus 3t is equal 0, so this is e to the 0. E to the 0 is 1. So x is this expression. Plus 2/27 plus c times e to the minus 3t. Okay. Okay, I think maybe if you want, we can, I don't know if you already did, but we can write simple solution of differential equation with separable variables, if you want. And so you are prepared for the next topic. And I will show you a brief example. Okay, so when you have something that includes a product of two functions, a product that means fraction in the expression of x dot, something like this. This is a very simple example. I don't know if I've taken this example from your book. So what can you write? You rewrite the x over dt, and you multiply and divide by everything that belongs to the same kind of variables. That means if you multiply both sides by x squared, you obtain a square times the x equals e to the 2t, and you should now take into account that the variable of differentiation, dt, could be seen again as something that you multiply by. That means you will obtain this expression like you divide, like you separate these two variables, and now you can integrate and use the dummy variable x on the left hand side and use the dummy variable t on the right hand side. And this is very simple because you can integrate x squared, and that will be x third divided by 3, and plus c, and we can put plus c in a constant that summarize both constant of the integration, and e to the 2t divided by 2 is the primitive of this function, and then you have plus t. So what do we have to find? We have to find x. That means that we can take x by rewriting x cubed equals 3 that multiplies everything. So 3 half e to t plus 3c, and then you can take the cube root, the third root of this expression on the right hand side, and you can give another name to the constant c and call a or c1 or c2, and rewrite something that is a constant that depends on the boundary values, and then you have your solution x. This is a very powerful tool to use, because if you recognize that you have the possibilities to split the product on the right hand side of the two variables, one depending on t, one depending on x, you can use this kind of trick, I would say. But I think you will see many examples with the professor during your lectures. So I think for today it is enough. Maybe you are tired, as tired as I am. And if there are not the questions, I hope you can understand everything. Maybe if you have something to ask, you can ask in the chat, or you can write an email, and I will send you these slides. These are and of today, so I will share with you in this chat. And as I said, if you have something to ask, feel free to ask, and I will try to answer your questions. Okay, I think there are no questions. Okay, fine. So, goodbye to everyone. I'm not sure which